Okay, so the title may be slightly provocative if this were a neuroscience community, but we're all here, most of you are familiar with Silicon Valley, and reverse engineering is very commonplace in Silicon Valley. But reverse engineering the brain is something that is actually quite important, and if you think of it, this is what the neuromorphic engineering community is really doing, has been doing over the last 20, 30 years. Right? They were making some progress, but it's slow. There have been several initiatives. Right? So, for instance, Karl-Heinz is leading or part of a major initiative in Europe on the Human Brain Project. There's another initiative here in the US, the Brain Initiative, which is geared more towards nanotechnologies for probing function on a very large scale. You may recognize, does anyone recognize here the neuromorphic engineer among the scientists? Yes, very on the left here. There's Strojanowski, right? Many would consider him the father of computational neuroscience. But he also was there from the very beginning at the Telluride workshops, has been very much an advocate for neuromorphic computing. Right? So relating neuroscience to engineering. There's another initiative that recently started, in fact, is more of a challenge than an initiative yet. So that one is more driven by computing, a challenge for extending computing towards difficult problems. And if you, it's hard to see, but so yes, what is highlighted here in the middle, right, is the challenge as formulated, right? So create a computer that basically learns and that does inference, right? And so there you would think, well, that's all good and well. So it's not what Google is doing. And in fact, last night, right, so a major feat of intelligence, of computer intelligence has been achieved by Google DeepMind, right? So you would think that to some extent this challenge is already met. But the clause here, an important clause here at the end is, do all this at the energy efficiency of the human brain. Right? And I would argue this is an important aspect because if you don't have a budget, if your budget is infinite, you can always do it. To some extent, you can think of what Google achieved, right? Has to some extent been a demonstration of massive resources. Right? So you may have heard the news. So last night there was a big, in fact, it's a big event or a big milestone, if you want, in digital computing. Right? So there was a match between the world champion Go and then Google DeepMind, because they were AlphaGo. Right? And so, would anyone dare to guess what was the outcome? So, man versus machine. Who won? For a long time, if you ask this question a couple of years ago, the answer would still have been, well, of course, humans can do this much better. This is a really hard problem in artificial intelligence, and it was considered, well, maybe we can solve this in 20 years from now, but it was a difficult problem. Well, so Google put things at work. So DeepMind, right, in a way solved the problem. And the outcome has been, indeed, so the machine won. So you can think of this as a victory of machine learning. But I couldn't help feeling also sorry for the champion, of course. Right? In fact, you can actually see how the emotional moment here, and the finger is the hand shaking at the end game here. Also, in a way, it's perhaps not a very fair comparison or a very fair match, right? So here you have the human being, right? So 15 or 20 watts of power in the brain. On the other side, you have this massive Google, right? So DeepMind with also deep pockets when it comes to power, right? So, and then this challenge, this new challenge is put out there, right? Is really trying to looking more at inspiration from biology in building systems that not only do the computation of what the brain is doing or get a cognition by computational principles, but also look at some of the physical principles, right, down to the physics of neural computation. Take inspiration from biology in building silicon systems and other systems that really can get there, right? And there have been some giants in the field who really have had very visionary thinking early on. Right? So Richard Feynman really started this revolution of nanotechnology. Right? In fact, he told us there's plenty of room at the bottom. And surely enough, Moore's law was really pushing things deep down all the way to the nanoscale. So that's where we're now. We're at the nanoscale. We went all the way from microns to nanometers, feature sizes. That has been great. So that has really been pushing the information technology revolution forward. Carver-Mead also has been pushing, to some extent, this information technology forward, right? By starting or by inspiring a VLSI approach to computing systems and to digital VLSI. Now, to that extent, they have been very instrumental in driving the IT revolution. But also, 20 years ago, those individuals, as long as John Hopfield and others, right, really started thinking about neuromorphic engineering, right, in terms of analysis by synthesis, right? So, and the Feynman's famous quote here is, right, what I cannot create, I do not understand, right? Only by building a brain would I be able to really understand how the brain works, right? And this concept of analysis by synthesis really also, right, contrasts the neuroscientist on one side and the engineer on the other side. Right? So science is typically about analysis, figuring out how things work. Engineering is about synthesis, putting things back together to make and make things that, so make new things, create new things that work. Right? And in the Brain Initiative, and more generally, if you want to understand how the brain works, it'll be important really to have this both approaches, analysis and synthesis, that work together, right, in order to make progress. Neuromorphic engineering take advantage of the fact that there are isomorphisms at the different levels of scale, right, going from ion channels all the way to the whole brain, right? And those isomorphisms at the physical level can be exploited, right, in then indeed synthesizing networks, so starting with ion channels all the way up to networks and the whole brain, right? So that's an important premise of what neuromorphic engineering is about. And Carver-Mead really started this field with a realization that some of the Boltzmann physics that we have of transport of electrons or holes across channels of a transistor, right, in a subthreshold regime. So when the transistor is below its threshold, these exponential currents as a function of voltage. They also translate to exponential conductances as a function of membrane voltage for ion channels, right? So for ion transport and across membranes, right? And this has been work by Hodgkin Huxley 60 years ago, and then Carver-Mead, so about 20 years ago, has realized, well, can't we then build circuits in silicon that emulate these physical principles also of ion channels and all the way up to other aspects? In fact, there's Boltzmann physics even at the network level in Boltzmann machines, etc. And there's been has been a great realization, and that really that started this field, and now 20 years later, it's actually now really taking off. Yeah. Even though one may argue there have been several waves of this revolution or this realization, and then perhaps much of the community is now focusing on algorithmic advances, but let's not forget that equally important are physical foundations of computing, right? If you want to get to the efficiency and the resilience of computing in silicon systems. There's some examples here, Bohanan's work on modeling, say, the optic nerve, right? So with spikes that encode important information in the visual scene through the optic nerve, right? And you can also do the same, right? So in this case here, you have temporal coding of events on the focal plane, implementing a computational imager. In this case, right, the threshold detection engine. Right? So when there's nothing changing, if the intensity doesn't change, if there's no change in the scene, there's no need to send any data across. Only when something happens, when there's a change in plus epsilon or minus epsilon change, right, that information can be coded and transmitted. Right? So it's good from a surveillance point of view for building systems, but also to some extent this can be thought of as a model or some model of temporal coding in, say, the optic nerve, right? Amacrine cells, and then some of the transient ganglion cells in the optic nerve, right? And there's some good arguments for temporal coding, and we have had a debate here, and it's great to continue the debate whether spikes are important or not so important, right? But I would argue that, and then there are several, so Giacomo also makes the argument that there are several of us, right, so that would look at spikes not just as an artifact of biology, clearly is an important artifact because that's how things are organized, right? But also as a means for efficient coding. For instance, Aurel Lazare was also showing some beautiful results on information theoretic views on coding using spikes and temporal information, right? Now, so there's one important aspect that needs to be addressed, and that's scalability in computing. And there I would argue that spikes are also very important, right? We have gray matter and we have white matter, right? So the gray matter is less than half of the brain. More than half of the brain is the white matter, the wiring that gets messages across, right? And so for there, spikes are extremely important. And temporal coding is important. But also an opportunity here that we have as from a computer architecture point of view, as Rajit Manohar yesterday showed us, is this asynchronous representation, this event-based representation that allow us to send messages efficiently across over large distances just by time multiplexing and taking advantage of the massive bandwidths that you have available in silicon, which you don't have in biology, right? So basically emulating white matter in a multiplexed, reconfigurable fashion, right, through these event-based representations on asynchronous buses, right? So where time represents itself, so neurons are encoded with addresses, and then so that data is presented on the bus that is inherent, so timing is inherent in representation. You need some arbiters on the sender side and some decoders on the receiver side, but other than that, it's fairly straightforward. Now, what has pushed the field further forward is the realization that this mapping, right, this white matter, can also encode then reconfigurable connectivity, right? So you can think of now as synapses as virtual connections that are instantiated as events on across this communication network. That can be so where the connectivity is then stored in lookup tables that specify connections between neurons, right? Now this is actually called flat AR because there's something that follows after it. But so this is work by David Goldberg at that time, 2000. So then the next generation of this was, so Jacob Vogelstein had also one next generation IFAT chips and had been some other ones. There's been plenty of work also by Giacomo's group. In fact, most of the chips I talk about here, right, so include also the facets, brain scale system, the Spinnaker system, True North, right? They all use one way or another this event-based representation, and also where synaptic information is then coded as entries in tables, right? So what you can think of here as this, what we call this an IFAT or an integrated and fire array transceiver, is this engine that does your SIMD type of the computation, right? What is SIMD here? So single instruction, multiple data. Every neuron more or less is alike. Of course, there's some differences, right? But each neuron is doing its integration of synaptic activity, and then is producing an action potential when it reaches a threshold or when something happens, right? So this modeling of the membrane and the excitability of the membrane can be efficiently done in analog or digital circuits, right? In array fashion, basically as efficiently organized as an array of cells that are addressable. And the synapses then reside in memory, right? And then because the synapses reside in memory, those are reconfigurable. You can change them on the fly. You can do plasticity and all that, right? So you can make systems. You can configure systems as in modular fashion to implement. This is an example here of acuity modulation, in which then you have a bottom-up and top-down model of saliency that is then used for modulating the resolution of transmission of in this case, in an imaging modality, right? Right, so combining, then in this case, a silicon retina chip then with one of those IFAT chips, right? Now, plasticity is extremely important, and we have already heard several talks highlighting spike time-independent plasticity, right? Now, this rule, because I don't have to go over it again, so we all know this, right? But if you think of it, it's really innately connected to an event-based representation because it's all about events, right? When an event happens, when a neuron fires, right, then something most likely will also happen in the synapse. And the relative timing of that governs, right, whether the synapse gets potentiated or depressed, right? Now, you can actually implement that rule, this SATP rule, very efficiently in this address domain, right? Because in your routing node that sequences and that routes spike events, there you have information available of all the history, right, over all the previous events and the current event, and based on that you can then dynamically change entries in the tables that are right at your proximity. In fact, this can be done also in hierarchical fashion. This can be also done very locally, right? So, and this allows a very efficient means for implementing learning, right? Now, let me say a few words, and perhaps not too much, on, so how do you get a cognition? And it's important for us to think also about cognitive systems. And so there are two important aspects of complexity that we have consider here. One is the task complexity. How difficult is a task? And on log scale, right, you would have a wide range here represented. Think of the very simple task here as, for instance, solving a spreadsheet in Excel. No offense to Microsoft, but that's basically a very simple task, right? It's very difficult for us, but it's a very simple task for computers. On the other end here, you have vision, or even just the simple things that, right? So just walking, because in the hallway, right, is a difficult task that even that is beyond the capabilities of most computers. Modeling, say, a fly navigation system has been elusive to computing. And somewhere, perhaps not all the way on the end here, but somewhere here would be, say, the game of Go, which has actually been tackled with a machine, right? So that's task complexity. And then on the other axis here, the vertical axis, you can think of that as Moore's axis. This is complexity, basically what you have to pay in terms of number of transistors, right, or power, etc., right? And typically we would think that the number of instructions that you have to do in order to say search in a if it's an NP kind of a hard problem, right, would be proportional. You would have to search through the entire space in order to find a solution. Sometimes with some problems you can have slightly better solutions using dynamic programming and the like, but still typically if you want an exact answer, right, your machine complexity scales with task complexity in a linear fashion, perhaps even worse, because Amdahl's law also tells us that you're right. So you're right in a very large system. Most of your activity is actually communication rather than computing, and then you lose performance. Neuromorphic computing can be thought as a means for flattening this curve, going more towards a favorable, well, not quite flat, but at least flattened representation, right? In which the same machine can handle more complex tasks with proportionally less work, right? And important there are two aspects. One is deep learning, and in fact we learned this yesterday night. What made Google solve the problem of Go has not been the same approach that IBM followed in the game against Kasparov, chess, right, which was very deep search. But here, this was deep learning, in fact, deep reinforcement learning. So combining deep learning of representations as well with the reward learning. Right? So Google DeepMind has been really able to crack the game of Go here and make the progress. Right? So you can think of it as a means for abstracting information from the environment, from data, right, in lower dimensional representations as something that will bend the curve down. Right? At the same time, it will be important for us to push, in terms of energy efficiency, push things on the right. So in the sense that for neuromorphic computing, right, it would be more efficient for us, or we have more bang for the buck, operating at higher complexities rather than lower complexities, since that where really neuromorphic can shine. It hasn't been shining yet, but hopefully in the future we'll be also solving very hard problems with neuromorphic systems. So far, if you try to compete against Microsoft doing a spreadsheet, there's no chance that their neuromorphic system will work. But perhaps for difficult problems like vision, or maybe also the game of Go, right? You may see neuromorphic computing shine. Right, so the important aspects, one is technology, scaling up to very large parallel systems, and then also learning, right? So, and the nice thing here is that you have those different disciplines that converge, right? It's no longer just the computer scientist or the computer engineer that is working here. It's really a convergence between different disciplines, both computer science or neuroscience, cognitive science, and then also device engineers to come up with better some solutions to some very hard problems of scale. And these problems of scale, right? If you'd like to go in a brain in a box, as what Dharmendra was telling us earlier, which was the hallmark of the Synapse program, it would be, right? So we have to really do something different from what we're doing today. Right? At the same time, also, computer science approaches are important too, but yesterday we learned that, to some extent, machine learning approaches may already be there. Now, for scaling to really work out here, it's important to also think of long-range connectivity, right? So our brains are not just SIMDs, SIMDs, right? We have also long-range connectivity, right? Even though most of the connectivity is local, the fact that we have white matter shows that there's also a significant portion of long-range connectivity that we have to account for, right? Getting the data across long distances. And for that, it's important to have some good information highways, or right, and so helper-based approaches in which you can have a more hierarchical means for sending data across these large distances may be a better way of doing it. Think of it this way, right? So between San Francisco and LA, right, there is a freeway. There's a few freeways. If you look at the cross traffic, right, along the Interstate 5, you may get perhaps right, at most a few hundred, maybe a few tens of cars per second passing through. Now, the total traffic within San Francisco, or just here in Berkeley, if you add all the traffic, is way more than this 10 or 100 cars per second. It's much greater, right? So you have a lot of local connectivity, local traffic, and you have much sparser traffic. But that sparse traffic is really important. You better make sure it is efficient, right? So, and you have freeways, you have airport terminals, you have, right? So it's important to organize your traffic in a hierarchical fashion. And tree-based approaches, right, will guarantee you a logarithmic distance, right? The number of hops you have to take to go a certain distance is logarithmic in distance, right? That scale better. Another important aspect than the expanse of the connectivity is also flexibility. How do you then code, right? So the capability of having refigurable logic. And so both need to be taken care of. And so a hierarchical additive representation is a means for doing this. There are several approaches that do this now, but so tree-based approaches for then building connectivity, right? So rather than having a random connectivity, well, which you may have in the brain, so you can structure this connectivity then through local hubs and hubs at different scales in which you have source coding. You only send the source address out, and then the next level up, that fans out. The fanning out, well, right, so there's little fan out going up in the hierarchy, and you have the greatest fan out going down the hierarchy, and the greatest fan out would be then at the lowest level, in which then you have all your synaptic connectivity, right? And also, you can only go up monotonically and then go down monotonically. You cannot cycle back and forth, and it's important. Otherwise, you would cycle, and you would possibly get some deadlock states. Right? So, developed a system higher. We call this higher hierarchical AR IFAT, right? In which we embedded these principles. Right? We have this hierarchical communication between units. And also then we have those analog chips. So now we have 65,000 neurons for each IFAT chip. Those are two compartments. So they're analog. They model then a continuous time dynamics with conductance-based synapses. And an important thing is that the energy efficiency of this is quite good. So we have about 22 picojoules of energy for each event, and also throughput through this IFAT chip of about 73 mega spikes per second. Right? If you compare this with other processors, right? You'll find, so there's a great diversity, analog versus digital, right? So general programmable versus, a more, massively parallel, or more biological versus more AI-driven, right? And many of those approaches, and so in fact, all of those approaches are presented here, right? And many of them have about the same performance, in fact. So we're all now at about picojoules per synaptic event, right? Which is orders of magnitude better than what you can do with state-of-the-art systems, whether it's CPUs or GPUs or FPGAs. Now, one important aspect of that is memory and the memory processor interface, right? And so it's important to then have the memories and processing interfacing closely. Fortunately, there has been recent developments in memory technology that are all based on whether it's resistive RAM or phase-shift memory, right? They're all basically conductors that are variable, that are based on activity, that are changed, their strength based on activity. You can really think of those as synapses, because after all, synapses are conductance-based, right? So rather than thinking of this element of this in this PCM, this phase-shift memory, as a bit in a table, you can think of it actually as a synapse, right? That is with presynaptic exponential that drives your word line, and then along the bit line, you can then integrate your activity, right? And so with Philip Wong here at Stanford, right, we're then developing extensions of IFAT circuits that have then the crossbar arrays on top for implementing then phase change, basically phase change memory synapses that do spike time dependent plasticity. Right, so this we can get much greater densities how much time do I have? We're done. Okay. So. All right, so to summarize, so you can also, in principle, can talk about just in a few words, right? So Wolfgang Maas told us some beautiful work on extending machine learning approaches to spiking neural systems, right? Using neural sampling. You can also do this. You can extend this neural sampling also to learning. Online learning using even a spike time dependent plasticity, in which actually two phases of this wake-sleep algorithm, the contrastive divergence, can be implemented with two phases of Hebbian and anti-Hebbian type of updates in your synapses, right? And actually, if you do that, you can get a performance of this network that is very close to the performance of Gibbs sampling in a Boltzmann machine. In fact, with synaptic sampling, in which now you replace the stochasticity that is just induced by having a Poisson neuron that couples to your neuron. If you replace that with the inherent stochasticity of a synapse, because synapses are stochastic, you have stochastic release. So now you get synaptic sampling, and that noise actually, that multiplicative noise, helps in this Boltzmann-like spike-based machine, right? So you get similar, in fact, you get better performance than Boltzmann machines, and you get also sparse network, you get sparse activity, sparse both activity and as well as connectivity in this network, right? So, and in fact, you get parity in the number of operations being done with, with these spikes, right? The synaptic operation done per second, versus the multiply cumulus that is done with Gibbs sampling on a computer. In other words, so the same amount of computation is being performed for the same for better performance, right? And I won't say anything about, so you can also go with extreme high efficiency, building then dedicated processors that have up to, well, this is actually teramax per milliwatt, which is actually 10 to the 15 operations per watt, or basically 10 to the minus 15 joules per operation, and that's actually the same level of efficiency as the human brain, but of course, the synapse does much more than just a multiply, right? And that's basically what I want to say.